Thank you very much for your introduction. My name is Isobe. I am from the unit of the Synergetic Studies for Space at Kyoto University. Dr. Shibata has already talked about the sun, but within the universe, the sun, is a planet. Sun is a star, about which we can take a lot of very interesting and very beautiful images. So this is the sun. This is the you shouldn't look at the sun directly, but by utilizing the filter, you will see this kind of sun, and you can see the sunspot. Other than that, this is very flat. And it seems to be very flat, but in reality, it is not flat. It is not static, so that the star is very close to the Earth as a fixed star. At the same time, it is an only fixed star, and whose surface observation can be done in detail. When it comes to other fixed star, they are so remote, and we can see them in a spot. But then the sun is an only fixed star, and about which close observation is possible. So in order to understand the space, we have to understand the sun. So this year is an International Year of the Astronomy to celebrate the 400th anniversary of the development, of the discovery of the sunspot by the Galileo. And this information was already presented by the Dr. Shibata. This is on day 25 and day 26, and you can see the changing shape of the sunspot. So the one important finding of the Galileo is that the sun is not a static one. It is changing constantly. So that this is another important finding of the Galileo. So in modern times, and we are observing very dynamic figures of the sun. At the time of the Galileo, so that they could utilize only the visible ray. So that this is an only wavelength of the wave. But today we are utilizing the satellite, and we are able to utilize different wavelengths of the electromagnetic spectrum. And you can see the different sun on the same day, but by utilizing a different wavelength, you can see the differences in the figures. So that this is a visible light. So that this red one are the figures with the X-ray, totally different from the figure with the visible light. And the orange ones, they are taken with the ultraviolet light, an extreme ultraviolet light, a shorter wavelength than the regular UV. So that this is visible, but this is an H alpha. So the spectrum, so that this is a kind of the special, so that somewhat different view can be obtained with this H alpha. And then the polarization, so that can be utilized, and then we can understand the magnetic field of the sun. So that the X-ray is flaring, but at the bottom you can see the black and white, and this is an X and N and S polars, and you can see the magnetic field. By utilizing a different wavelength, and we will be able to see the sun in a different manner. So I'd like to show you the different images of the sun. So that this is so that the most important image in the history of the the astronomical physics. So that this is a Yoko satellite launched by Japan. So that this is a figure of the sun in the X-ray. And the X-ray is not necessarily red, and this color is artificially given. So in the space, so X-ray, so that can be obtained in order to take a picture of the sun like this. So the right-handed side, and you can see just a regular sun figure with a regular light, but totally different figures between the two. So that with the X-ray, and you can see a lot of flares as well as an exposure. So that the red area shows high, so that the energy field. So as you can see, the sun is very active and very dynamic. So that this was confirmed with the observation with the Yoko satellite. So that this is SOHO launched by the US and Europe, and then this is taken with the ultra EUV. And so that here you can see the flashing, so that the kind of a loop, it is generating and dissipating, and this is a flare with the X-ray, and more minute details can be observed. So that this is flashing, but very minute structures are there. So that why those phenomena are happening, so that this is an important purpose of our discipline. So that this is somewhat different, so that the wavelength is visible light, but from the space, from the satellite, so that we try to utilize so that the device in order to mask the sun, so that the white spot represent the location of the sun, but in the space there is no air, no oxygen. But because of the absence of the oxygen, so that we can observe so that the light of the sun as well as the flow of the plasma. So that there are little spots, so that flowing from the left to right. Those are so that the ostensible movement of the suns. But please take a look at this UFO-like so the object. It is coming from the right to the left. So that this picture was taken with the satellite of the NASA. So it was up on the homepage, and it is updated, and so that this was so that deleted on the next day. But one religious organization made an announcement that so the NASA found a UFO. This is very dangerous, and this has to be deleted immediately. But this is not a UFO, but this is a planet. So that the planet is moving in relation to the sun or in relation to the earth. So the movement is different, so that in the case of the planet. But in Japanese, and this planet is so that expressed so the star at a loss or the star perplexed. That is so that that is because the planet is moving in a different manner. So, and you can see so the plasma flowing from the sun. So if there is a flare or the eruption, and you can see so the more dense, so that the flow of the plasma released into the space. So that the eruption, so that due to so that the explosion might be coming to the Earth, and which might have an impact on the Earth. So I'd like to give you a more close-up view of the sun. So that this is taken so that with the Hira Observatory of the Kyoto University, so that this is an HR, and you can see some kind of the color so that layer, so that this is a flare location. So that we are showing a more zoom-up view of the flare on the right-handed side. So that there are two spots. In between, there is a phenomenon of the explosion. So this solar flare is the biggest explosion in our solar system. So that it is an equivalent to 100 million of the hydrogen bomb, and this is very potent. So let's look at the solar flare in the EUV taken from the satellite. Very beautiful. So that the image, and you can see the edge of the solar. There is an explosion here. And then something is going from the left to the right. And then you can see the loop-shaped structure. So now when there is a flash, there is a kind of a noise of the image, and the image is very much disturbed. This is because of the high energy irradiation so that generated due to the explosion, so that so that the high energy irradiation reaching the Earth, attacking the CCD camera. This is because of the noise of the images. So this kind of high energy irradiation is happening, but if the astronaut is flying in the space, so that this is very damaging and very lethal to the astronaut. So this is a very beautiful, but potentially very dangerous and lethal phenomenon. But of course, and as long as we are on the Earth, we will be safe. But the astronaut might be at a risk. So that this is a satellite view of the surface of the solar, the sun, and you can see the edge, and the flare is not so active, and you can see eruption, and no so the radiation, but then you can see the eruption occasionally. So I have talked about the flares as well as solar wind, as well as the eruption. So that what is the reason, what is the cause of such a dynamic activities of the sun? This is because of the magnetic field. So that this is schematics showing the magnetic field. So solar spots are a big magnet. So that so the white is an N and the black is an S polar. So that by connecting between the two, so that you can see the loop structure in the EUV, so that this is as if a magnetic field line when we place a bar magnetic in the sand. So that the sunspots are the so that the magnetic so the polars and the magnetic field line is represented by the loop structure. So what we are going to study so that there are three major challenges for our discipline. And the first is what is the reason for the existence of the magnetic field on the sun? So that this is the largest and the most challenging and so the issue we'd like to solve. But we can see it in the X-ray and the others. That means the outside of the so that the sun is heated up to so that the 1 million degrees Celsius, and please add one more zero. There is a type of mistake on the surface of the sun, so that the temperature is about 6,000 degrees so that Celsius. But then how come outside is more than 1 million degrees Celsius? And maybe this is associated with the existence of the magnetic field. And the last one is flares, because they might affect our so that the Earth. So that what causes an explosion, and can we predict them? Those are the challenges of our research of the solar physics. And the images are quite important in order to find a solution to those problems. And I'd like to show you more recent images taken with the newer so that the satellite. And Japan and UK and Europe, as well as UK, US, and Europe and Japan work together in order to launch a new satellite called Hinode. And this launch was in September of 2006. This is dedicated to the observation of the so the sun, so that you can see X-ray, so that the telescope. And then there are three different types of the telescopes in order to observe the sun very closely. So that this is an observation of the sun from the Hinode. This is in the visible light. So if you have a vision acuity of the 300, and you can see this kind of sun with your naked eyes. So that this is before the sun, so that the rising. But so that this is in the vicinity of the solar spot. So the black one, that there is a penumbra. So that this is a stripe, so that like so the vicinity, and the outside, then there are the bubbles like forming. So that this is a kind of a thermal convection. So that this movie, so that is given the encouragement prize of the academic film competition. So that this is taken from the Dr. Okamoto from the National Observatory.
Now, this is also the image taken by Hinode. And there was a flare and the same data as shown before, but slight difference. And inside the sun, the calcium atoms do exist, as well as calcium ions. From those atoms, a specific light is emitted. As a result, that a slightly upper layer of the sun surface can be now visualized, and you can see the sunspots. This is a magnet, therefore that draws a lot of energy. When the accumulation of energy is reaching certain point, it is gradually released, which causes a very, very violent phenomenon. You can see very bright structure or flare. It is almost like explosive, and the cosmic jet was mentioned, and the gas is actually emitted straightforwardly. Therefore, it is the jet phenomenon. So the solar surface jet phenomena can be examined, as a result of which, and we can actually elucidate the enormous jet phenomenon which sources and derives from the black hole. Because of that significance, and we are very committed to this research. This is based on the calcium and ion-based observation. It is over and above the sunspot, and very enormous and giant flares were provoked. This shows two sunspots, and there is a difference in the altitude, but between the two there was an enormous flare, and you can see the bright location. It was one of the big flares which happened in the sun. When such a phenomenon happens, there is of course an impact to us. For the human beings and also for the globe itself, what sort of influence is given by the sun? Space weather is one academic category in which research interest is converged more and more, and there has been some progress made in this discipline. Once the flare occurs, and a high energy cosmic ray and radioactive ray is emitted, so that causes damages to spacecraft as well as astronauts. Therefore, we need to continue the monitoring and the measurement of the sun. Not only the high energy, but also you remember that the corona, which was an outer layer, and also emittance of gas. That gas clutter is visualized now, which is oriented to the Earth. Then it collides with the Earth's magnetic field. And you must have had the electromagnetic induction experiment when you were at school. So when there's a collision occurs, and the electromagnetic current is provoked and around the surface, and when that current reaches the poles of north and south, aurora is caused, and also the magnetic storm is caused, and the EMI might be provoked, and also there might be damage to the pipelines and also the transmission lines on the ground on the Earth. And therefore, aurora is positive because it is in a good sightseeing spot, but some negative points are also known because there might be some damages. So we would like to have some weather forecast or space weather forecast as we do for the Earth itself. This was prepared by the NASA. The relations between the sun and also the Earth is represented in the animated picture. It is not a representation of the observatory data. So there was a collision between that and a gas cluster and the magnetic field of the Earth. Then inside the magnetic field of the Earth, there's another smaller size flare. When such an image is actually established in this animated picture, what we are interested in the forecast? And can we actually have the space weather forecast? In the solar system, the imaging is very important. The image-based observation is very important. What we want to know is the dynamic phenomena of the sun, not the static one. In order to understand the sun, we need to focus our attention to dynamism and dynamics. Every day at various observatory stations, an enormous and giant volume of data is created. It is published almost right away. So because of that enormity, it is almost impossible for us to see all the data. What do we do then? When the data is collected, then we can transform it to images. Then when we stare at the images, and we can find something exciting and inspiring, that would be the very important starting point of the solar study. Hinode made a very large, important discovery, and one of them was the discovery of Alphen wave. So this magnetic ray is actually oscillated like guitar strings. So oscillation of the magnetic field lines was discovered inside that solar atmosphere. That was the biggest discovery. You can see the arrow, and can you find the Alphen wave? Maybe it's hard, but when you transform that data to images and the animated picture, you can see the oscillation very, very clearly. So the upward and downward movement. So this is in line with the magnetic field lines. If you identify these images, you can find this phenomenon right away. But if you just stick to the static images, it would be very difficult for you to identify such a phenomenon. And oscillation phenomenon can be also found like some rubber band loops, and they are oscillating and undulating. So that was actually identified and discovered through image observation. I would like to talk about the mathematical simulation and numerical simulation. Theoretically, the solar phenomenon can be reproduced in the computer. In order to do so, we focus on some block of the solar phenomenon, and then inside that box, and we create the grids. And then in those grids, we establish magneto-hydrodynamic equations, and we try to get the answer to those formula, each of the formula. And the result of the simulation is this huge, long list of numerical figures. So imaging is very important. This is a simulation of the cosmic phenomena. The sun is an ever-changing star. Dynamic phenomena is in the center. So because it is dynamic, and we need to look at the image, which is derived from the enormous amount of accumulated data. What is the challenge in front of us? So observatory data is accumulated everlastingly. So I believe that an image is actually a space and a plus and a time, but actually four-dimensional, because you can identify, you can add more parameters like density, temperature, and also magnetic field. So in the end, you will have the fifth dimension and also five-dimensional world. So we would like to get some tool which is much more than the ordinary conventional imaging tool. That is what we want, and also challenge. Thank you. Thank you very much.